This mini-lecture addresses the key ideas behind line integrals. The line integral is an important mathematical tool for solving physical problems. It's usually used in introductory or intermediate physics courses to calculate the work needed to move an object from one location to another. Despite the fact that it's useful and commonly used, many students have difficulty setting up and calculating physical line integrals. This lecture addresses the what, the why, and the essential how of line integrals. Examples and special cases are worked in the next two mini-lectures. In physics, line integrals can be used to calculate the distance along a path. For example, if we want to calculate speed. They are used in a mechanics course to calculate the work to move an object from one point to another, and in electrostatics to calculate the change in potential energy moving from one point to another. Line integrals are important also in electrostatics for the applications of Ampere's law and Faraday's law. What is a line integral? A line integral is the sum of the value of a function along a specific path or curve through space. The function can depend on position in space, x, y, z, and Cartesian coordinates. The path is frequently labeled in the limits of the integral with the word curve or the letter c. The curve, or the path, is given by the relationship between x, y, and z along the path. We limit our consideration here to a path in x and y because it's easier to draw and in order to focus on the key ideas. A special line integral in physics is the work to move an object along a path between 2 points. The work is the dot product between a vector field, a force, which is a vector that depends upon position, with a distance element along a specific path. Let's look at each of these elements in turn. A vector field is represented here as an array of vectors, an array of arrows at each point. The magnitude of the field at each point is represented by the length of the vector, and the direction is represented by the arrow direction of the vector. The formula for the vector components for this example is given on the right. We might calculate the work done moving along the path represented by the moving red arrow. That path has to be represented by a functional relationship between x and y. Okay, we have the field. Now we want to describe the path. The vector ds is an infinitesimal step in a particular direction. I've written it as a delta s here because it's finite. We would take the limit of delta s being very small in order to do the integral. That step, delta s, can be written as a step in x and a step in y. The direction of the step depends upon the relationship between delta x and delta y for that particular step. And the vector delta s, ds, is just the vector sum of the step in x and the step in y. The actual path from one point to another depends on the relationship between dx and dy, which depends on the relationship between x and y along the path, usually given by a function. Here's an example. For a curve, y is equal to g of x, y, position in y, is equal to g of x. The relationship between dy, that is the step in y, and dx, the step in x, is given by the slope of y with respect to x, that is dg dx, because y is g of x, times the step size ds. Now we have the relationship between the infinitesimal steps in x and y that give ds. We can then make a substitution and write ds completely as a function of x or y as we prefer. ds here is written entirely as a function of x. It could also be written as a function of y. The next step in calculating the line integral f dot ds over some path for work involves the vector, scalar, or dot product. In this example, F has magnitude, the force at that particular point has magnitude and points in this direction theta, at an angle of theta with respect to the path step ds. F and ds have different units, so drawing them on the same graph is a little bit problematic, but I hope that you get the idea here. We've got the direction of ds. The dot product is the projection of F onto the direction of ds. F cos theta times ds. So the dot product is just F cos theta ds, can be easily found if theta is known. Now, you can also perform dot products using the fact that ij and k unit vectors are perpendicular to one another. So I dot j is 0. Of course, I dot I is 1. Let's go through it step by step. The force, Fx, can be written in two components. The component of the force in the x direction and the component of the force in the y direction. That gets dotted into the step ds, which is I dx plus j dy, yielding F sub x, the force in the x direction dx, plus F sub y dy, which can be split into two integrals from the start point to the final point along the curve, f of x dx plus f of y dy. We now have two integrals, one in x and y, but the functions in the integral, fx and fy, might actually still be separate functions of x and y. So we need to simplify, we might need to simplify further. Remember that the relationship between x and y is set by the path that we do the integral over. So for a given path, coming back to y equals g of x, and there's just a path sketched here, f of x, that is the force, can be written solely as a function of x by making the substitution y equals g of x. So these are our two positions in Cartesian coordinates, x and g of x. And the relationship between dy and dx can be found by, again, taking the derivative of g with respect to x. So that integral over the curve, f dot ds, can now be rewritten as f of x, which is a function of x and y, dx, f of y, function of x and y, dy, and making the substitutions for the components dx and dy and y for x, we end up writing the entire line integral in terms of one variable. Then we only have to worry about where we started and where we ended. The actual path is taken care of with the functional relationships between y and x. What are some things to keep in mind when you actually need to start working on a line integral? The so-called tricks of the trade. First, line integrals can always be written in terms of the integration over a single variable by making the kind of substitutions that we just did. But before you start, spend some time thinking about how to choose that variable before proceeding. Second, sometimes it's easiest to divide a path up into simple pieces, each expressed in terms of a different variable. We'll show you an example of that later on. And finally, in special cases, the value of the integral doesn't depend upon the path chosen. We'll discuss how to identify these cases and how they can make calculation easier in the third mini lecture on line integrals.